Hello guys, good morning. Good morning everyone. Good morning, can you hear me? Am I audible? Hello? Can you hear me everyone? Yeah. Good morning all of you, good morning. So, welcome back to the sessions, and this is going to be the final session in YouTube live classes, and hope you have finished all the portions and you are waiting for the final revision part. And today we are going to have a quick run through the topics, all the topics, and we will be discussing all the questions, all important points. We won't have time to discuss this, but we will just go through the topics, every single topic. And if you have missed any of these points, you can have a quick revision after this. Okay, good morning everyone. Devika, good morning Jesse, good morning Chris, Gayatri, Sadiq, Martin, Gayatri, all of you, Dia, all of you. Good morning everyone. I'm clearly audible, right? Okay, right. So let us start. Let us start with the first topic, electric charges and fields. Now these are the important parts in electric charges and fields. First one is Coulomb's law. What are the probable questions from Coulomb's law? Coulomb's law is force between two charges is given by K Q1 Q2 divided by R square. K Q1 Q2 divided by R square. They might ask a numerical like this. They'll put three charges on a triangle. One charge here, one charge here, one charge here. Plus Q, plus Q, plus Q. And they'll ask you to find net force on one charge. How to find it? Find the force by this charge on this charge. Find the force by this charge on this charge. Find their vector sum. So you can expect such a question. Another one based on this is, what are the charges? What is the value of this charge? If these two charges are kept at the ends of a line and the system is in equilibrium, the charge in the middle is minus Q by 4. Minus Q by 4. That's an important question based on Coulomb's law. And if Q1, Q2 is less than 0, what does it mean? Q1, Q2 less than 0 means, the product is negative. Product is negative means force is negative. Negative force represents attractive force. What if Q1, Q2 greater than 0? That's an important question. Q1, Q2 greater than 0 means this is positive. That is positive means force is positive. Force is positive means it is repulsive force. So the charges will be identical. Q1 and Q2 will be either plus or minus. Got this? All of you got this? Everyone? Right. That is the first point. We can't spend too much of time on this. So these are the probable questions from Coulomb's law. They might ask the statement of Coulomb's law or this one. Force is equal to K Q1 Q2 divided by R square. They will say the charge is doubled, distance is halved. What will happen to the force? So how do you write it? First, Q1 Q2 by R square, first force. Second force, you write F dash equal to K into 2Q1 2Q2 divided by R square is R by 2 the whole square. That is an important question. So this is all they could ask from Coulomb's law. The statement on Coulomb's law and net force problems, equilibrium question, then Q1 Q2 less than 0, Q1 Q2 greater than 0. Alright, and the force modified by variation in charges and the distance changes. Alright, you can see this in the link later, in the YouTube channel later, or you can take a screenshot right away. Shall I go to the next point? Shall I go to the next point? Everyone, make it quick. Okay, I'm wiping it. Alright, so let us move to the next point. Next point here is electric dipole, torque, work, potential energy. Electric dipole, what all questions can come? Electric dipole, they can ask the derivation. Axial field is what? K into 2p by r cube. K into 2p by r cube. Okay, K into 2p by r cube. Electric field axial is given by K into 2p by r cube. Axial field of a dipole, this is very, very important, and equatorial field is equal to P by R cube, Kp by R cube. And what do you understand between these two? E axial is equal to 2 times E equatorial. This has very high chance of coming as an MCQ. E axial is equal to how many times E equatorial? Equatorial point. If this is dipole, this is called an axial point. And this is called an equatorial point. Axial field will be double the value of equatorial field. Okay, double the value of equatorial field. Now this is a derivation. It will come for 5 marks or 3 marks. Axial field and equatorial field derivations are very important. Very important. Okay, shall I move to the next one? Make it quick. Responses quick so that we can finish on time. Alright, we can't take too much of time. Alright, so next one. You know, they will ask the questions on torque. You know, they will ask you to derive the equation for torque. Torque is given by P sine theta. Torque is given by P sine theta. The derivation is very important. Derivation. P is dipole moment. E is the electric field. Theta is the angle. So this is the electric field dipole placed in an electric field. What kind of electric field? This is a uniform electric field. Uniform electric field. Okay, so you can write in vector form as vector P cross vector E. Once there was a question in board examination, identify the perpendicular vectors. You know, here tau will be perpendicular to P, tau will be perpendicular to E. Why? Because in cross product, you learned in mathematics, in cross product, result will be perpendicular to the component vectors. Perpendicular to the component vectors. So, tau perpendicular to P, you can say tau perpendicular to P, tau perpendicular to E. Identify the pairs of perpendicular vectors. That is an important question. Then torque based numericals. Easy. Torque based numericals. They will give you P value, they will give you E value, theta value, you just have to substitute and find out. And dipole moment is what? One of the charges multiplied by distance between the charges. Many times in examination, this question has come. Define dipole moment. Direction. Conventionally, you go to any part of the world, direction of dipole moment is conventionally taken from negative to positive. Okay, negative charge to positive. Dipole moment is taken from negative to positive. Unit is what? Unit is coulomb meter. All right, this is dipole's torque. What is the work done to rotate the dipole? This derivation is also important. Minus PE into cos of theta 2 minus cos of theta 1. You know, you are rotating a dipole from theta 1 angle to theta 2 angle. Initially the dipole was at theta 1, you rotated it to theta 2. What is the equation? Minus P into cos theta 2 minus cos theta 1. When you put theta 1 90, because the 90 is reference. When you put theta 1 90, then tell me, W will be what? Minus P E cos theta. This is called potential energy. So potential energy is minus P dot E, because AB cos theta is A dot B. AB cos theta is A dot B. Potential energy is P dot E. Then stable equilibrium and unstable equilibrium conditions. Stable equilibrium. What is meant by stable equilibrium? Theta is equal to 0 condition is called stable equilibrium. If a dipole is kept parallel to the field, theta is 0. You know, unstable equilibrium is what? Theta is 180. Stable to unstable or unstable to stable. They will ask you to find the work done. Work done to rotate a dipole from stable to unstable or unstable to stable. Stable to unstable or unstable to stable. Stable to unstable. Stable, theta 1 is 0. Unstable, theta 2 0. Put them over here. Theta 1 is 0 and theta 2 is 180. Okay, you will get 2 PE. That will be the work done to rotate the dipole. You can find the work done to rotate the dipole. Okay, and then the third point. Shall I wipe this? You know, the third point. If you keep a dipole in a uniform electric field, look at that, uniform electric field. You know, look at the dipole. Torque is not equal to 0. There is a torque acting on it. What about the force here? Force will be 0. Why? Because force here is to the right, QE. Force here is to the left, QE. So what is the net force on it? If they are projected to the center of mass, net force will be 0. So if kept in a uniform electric field, remember that word is important. Uniform electric field. If you're keeping the dipole in a uniform electric field, you know the net net force will be 0. Torque will be not equal to 0, which means there will be rotation but no linear motion. No linear motion. But on the other hand, if you keep a dipole in a non-uniform electric field, look at this non-uniform electric field. This force is QE, this force is QE dash, then the net work done is what? Net force is what? Net force is not equal to 0. Torque is not equal to 0. This question has come 8 times in competitive examinations and 3 or 4 times in board examinations. A dipole placed in a uniform electric field. Option A, tau 0, F 0. Option B, tau 0, F not equal to 0. Option C, tau not equal to 0, F equal to 0. Option D, tau not equal to 0, F not equal to 0. Uniform field, tau not equal to 0, F equal to 0. And non-uniform field, F not equal to 0, tau not equal to 0. That means dipole will have both linear motion and rotational motion. Rotational motion, that's all about dipole. Right, let's move to the next one now. See this. Hope it's clear. Right, moving to the next point, stable, unstable. I did Coulomb's law, I did electric dipole, stable, unstable I did. Now axial, equatorial I did. Field lines diagram properties. Field lines diagram properties. You know, field lines, you know what? Field lines are drawn from positive charges, right? Field lines are actually what? This actually gives the direction of electric field lines. Now properties, there are 9 properties. Number 1, field lines originate from positive, they terminate on negative. They terminate on negative. Okay, field lines can be straight or curved. Straight or curved. If it is curved, the direction is given by the tangent. The direction is given by the tangent. And then field lines are perpendicular to equipotential surfaces. Field lines are perpendicular to equipotential surfaces. And field lines will never intersect. Never intersect. Why? Because if field lines intersect, at this point there will be 2 tangents. Can you be here and in India at the same time? No. So similar way, the particles cannot go in 2 directions at the same time. Particle cannot go in 2 directions at the same time. So electric field lines can never intersect. That's one of the most important questions here. Electric field lines can never ever intersect. Why? Why? Because if they intersect at the point of intersection, the field will be 0. And then closer the field lines, stronger the field and vice versa. Closer the field lines. If the field lines are close, that means the field is strong, and vice versa. Alright, and vice versa. Okay, and then if like charges are brought close, tell me what? Like charges are brought close, you know, look at this, brought close like this. There will be lateral expansion of field lines. Field lines are getting repelled. This is called lateral expansion of field lines. And if unlike charges are brought close, there will be longitudinal contraction of field lines. Longitudinal contraction of field lines. Okay, so that's all from field lines, electric field lines. And next point is Gauss's theorem. Obviously, Gauss's theorem is one thing to watch out for. Gauss's theorem is so important. This year, let me promise you, I promise you there will be a question from Gauss's theorem. Gauss's theorem is what? You know, you have learned flux is given by 1 by epsilon 0 into Q. Q enclosed. Flux coming out of a Gaussian surface is equal to 1 by epsilon 0 times the charge enclosed by the Gaussian surface. Okay, so the applications, there are 3 applications. Number 1, due to a spherical shell, electric field due to a spherical shell, outside inside surface, outside inside surface, and the graph is very important. This is how you draw the graph. Inside electric field is 0. Inside electric field is 0. Inside electric field is 0. The graph is very important. Okay, outside kq by small r square, surface kq by capital R square. Then number 2 is due to a sheet of charge, infinite sheet of charge. Okay, infinite sheet of charge, this is sheet of charge. Okay, due to sheet of charge, electric field is given by sigma by epsilon 0. Sorry, sigma by 2 epsilon 0. Sigma by 2 epsilon 0. Sigma is called surface charge density. Surface charge density. Alright, and what is the nature of the graph? As you can see, sigma, this electric field is independent of distance. Do you see any distance in it? Do you see any distance in it? No, I don't see any. You don't see any, right? Yes, electric field is a constant. Electric field is a constant with the distance. Electric field is a constant with the distance. That graph is important. Okay, and you know, third question is this. You know, due to a line of charges, the electric field at this point is what? It is given by lambda by 2 pi epsilon 0 r, where lambda is called linear charge density. Linear linear charge density. Lambda is called linear charge density, charge per length. And the graph is what? If you draw E against R graph, this is how the graph will look like. Because electric field and distance are inversely proportional. Electric field and distance are inversely proportional. And is that clear, everyone? Can I have a response, please? Everyone, please. I'm about to end this topic. That topic is finished. I'm moving to the next one now. All of you got this? Right, hope you got this. I'll tell you the numerical from this. Important numerical from this. One question, obviously every time that question is asked. The reader question, in the reader they have given this. You have a cube kept in a coordinate system like this. And in the reader example question, they have given electric field as alpha x raised to half, where alpha is 800 in the question, 800 in the reader question. 800. X is this distance, x is 0.1. This distance is 0.1, this distance is 0.1. Last year also in foreign paper they had this question, electric field is equal to A plus lambda x. There are many questions asked on this, but remember, flux on the left side is non-zero, flux on the right side is non-zero, flux on the top is 0, flux at the bottom is 0, front is 0, back is 0. Just imagine a river is flowing. A river is flowing to the right. So left surface and right surface will have something to do with the flow, right? So here river is my flux. So the top surface, bottom surface, back surface, front surface, they got nothing to do with this question. Right. So you calculate the flux, then electric field you can calculate. This is an important question. Take my words. This is very important question. And second one, they will ask this question. You are keeping two charged placed like this. Positive, negative like this. What is electric field here? What is electric field here? This plate has plus sigma, this plate has minus sigma. Electric field here is 0, electric field here is 0, electric field here is sigma by epsilon 0. Now this setup is known as a capacitor. We have learned this. The derivation is very important. Many times this has come in examinations. Electric field outside the plates is 0, electric field outside the plates is 0, electric field in between the plates is sigma by epsilon 0. That's all from first topic. Shall I move to the next one now? Everyone, all of you. Can I have a response, please? I'll make it quick. Right. So you can, yeah. We'll move to the next slide now. This is what? Yes, this is, potential and capacitance. Electric potential. What are the probable questions there? Two important derivations. Okay. One is derivation of potential of charge, potential of dipole. Look at that. Potential of charge. What is potential due to a charge? KQ divided by R. Potential due to charge is KQ by R. Potential due to dipole is KP cos theta divided by R square. They will ask you to derive both. But when deriving this second one, they will ask you about axial field and equatorial field. Axial potential. Axial potential, equatorial potential. Axial potential means, look at this. I did this for a random angle theta. Right. So for axial, theta will become 0. You can put theta 0. You will get Kp by R square, axial potential. What about equatorial? Equatorial. Look at this angle. That angle is 90. Put cos 90. Cos 90 is what? Cos 90 is 0. Tell me guys, please. Cos 90 is 0. Tomorrow is going to be the D-Day and you're going to make it. 100% sure. Trust us. You're going to make it. You're going to come out in flying colors. 100% sure. Okay. Just trust us. Okay. Now Kp cos theta by R square. What is E equatorial? V equatorial is equal to 0. That means for a dipole, on the equatorial line, everywhere potential is 0. That is an example for equipotential surface. This is an example for equipotential surface. Equipotential surface means what? Potential is the same everywhere. For a dipole, the best equipotential surface you can memorize is, equatorial line. Let's go to the next point now. So that point is done. Derivation of potential. That's a 5-mark question. Very important one. Okay. Work done, potential energy of dipole. Work done, already done in the last chapter. I did it in the last chapter. Work done is minus PE into cos theta 2 minus cos theta 1. Potential energy is minus PE cos theta, minus PE cos theta. Then stable, unstable. I already did stable, unstable. Next is potential energy of a system of charges. System of charges. What is potential energy of a two-particle system? Potential energy of a two-particle system is K Q1 Q2 divided by R. Two-particle system. It is the work done in assembling the charges to their present separation from their infinite separation. Initially the charges were infinitely separated. Now you are bringing them closer. The work done is potential energy. For a three-particle system, it is K into Q1 Q2 by R1 2 plus Q2 Q3 by R2 3 plus Q1 Q3 by R1 3. You can expect a numerical on this also. First, second, third, first, third. Three-particle system. Okay, three-particle system. Technical term, please. Okay, no problem. Third, three-particle system. All right, this is potential energy of three-particle system. Potential energy in an external field also may be asked. External field. That is a small derivation which you have to learn. K Q1 Q2 by R plus Q1V plus Q2V. You must have done this. Q1V plus Q2V, where V is the potential. This is potential energy of two-particle system. Potential energy of three-particle system. Potential energy of two-particle system in an external electric field. In an external electric field, these two terms are coming up. An additional term Q1V, an additional term Q2V, one for Q1, second one for Q2. All right, so let us move to the next point. Equipotent surface properties. Equipotent surface properties. You know, what are properties of equipotent surface? From equipotent surface, they can ask which all questions? What are equipotent surfaces? Number one, equipotent surfaces. From the name itself, it is clear. It is a surface on which potential is the same. Surface on which potential is the same. Number two, properties of equipotential surfaces. Properties. I'll tell you 5. You need only 4. Number 1, equipotential surfaces have same potential everywhere. Number 2, potential difference is 0. Potential difference is 0. Number 3, work done to move a charge on equipotential surface is 0. Work done to move a charge on an equipotent surface is 0. Alright, that is an important point. On an equipotent surface, no work is to be done. Fourth one, equipotent surfaces will never intersect. Equipotent surface will never intersect, because if this is equipotent surface, I can draw the field lines. These are the field lines. If equipotent surface intersect, field lines also intersect. But we know that field lines cannot intersect, right? So equipotent surface cannot intersect, and field lines are always perpendicular to equipotent surfaces. Field lines are always perpendicular to equipotent surfaces. And the last question, they will ask you to draw equipotent surfaces. First one, point charge, all spherical surfaces. Okay, you can also draw the field lines. Okay, draw the field lines. And second one, uniform electric field. Uniform electric field, any surface held perpendicular is equipotential. Any surface held perpendicular is equipotential. Third one, for a dipole. For a dipole, this is how you draw it. First one, you have to draw a circle like this. Second one, little elongated this way. Oh, I don't have space there, but anyway, I'm just drawing. This is how you draw it. I'll draw a better figure, but time is a problem. But anyway, I'll draw it. Look at this. You know, this is positive, this is negative. First one is a spherical surface. Second one is little elongated this way. Oh, sorry, the other way. Little elongated this way, and next one is this way. This one is equipotential. That is for a dipole. And what about identical charges? First one is a sphere. Second one is a sphere elongated this way. It is elongated closer to each other. And third one is this. All right. This is purely mathematical. You can't say why it is looking like that. But if they ask a question, it's going to be the figure itself. And fifth one, this time there is another one for a line of charges. A cylinder is equipotential. Equipotent surfaces. Okay, then you can expect a question on equipotent surfaces. Look at this. They'll give a coordinate system. They'll say one particle is kept here at a, 0. What is the work done? This is plus q. Another charge is in the middle, origin, plus q. What is the work done in taking this charge to minus a, 0? What is it? Actually, these 2 points are on a circle, right? That circle is an equipotential surface. So work done will be what? 0. Work done will be what? 0. Or a charge is at the center, another charge is taken in a circle. What is the work done? Work done will be 0. Work done will be 0. That is an important question. Now moving to the next one, this is also done. Then derivation of capacitor, combination based numericals, effects of introduction. Capacitor based questions, I'll go in a stretch and then I'll hand over this to Rafi sir, who will be taking magnetic effects questions. Okay, now capacitors. First one, parallel plate capacitor. Capacitance of a parallel plate capacitor, epsilon 0 A by D. Before that there is a graph, Q against V graph. Graph is straight line, direct proportionality. Two questions. Number one, slope of the graph. Slope of the graph is what? Y axis by x axis, y axis by x axis, y axis by x axis. So slope of the graph is what? Y axis by x-axis, Q by V is called capacitance. Okay, they might give a figure like this and they will ask you to find the ratio of capacitances. This angle 60, this angle 30. Take tan 30 by tan 60, tan 30 by tan 60, tan 30 divided by tan 60. Second question. All right, second question, you can find the area under the graph. Area is what? This area looks like a triangle. Triangle's area is half BH. When you find it, that's going to be energy. So slope of the graph is capacitance, area under the graph is energy. Slope of the graph is capacitance, area under the graph is energy. Then the derivation of this is important. Then combination of capacitors, series combination equation, this derivation, 1 by C1 plus 1 by C2 plus 1 by C3. Parallel combination, C1 plus C2 plus C3. The combination based numericals, particularly this one, if it is taken top bottom, it is parallel combination. If it is taken left right, it is series combination. This is parallel combination, this is series combination. And if it is given this way, take this as one capacitor, K1. Dielectric constant is K1, epsilon 0 K1 A by 2 by D by 2. Then this one, epsilon 0 K2 A by 2 by D by 2. Then take them in series first. Take that in parallel with this one. That is an important question. Previous question, 3-mark question. Okay, 3-mark question, it's important. All right, now series parallel combinations, energy. Then when a slab is introduced, capacitance with a slab introduced, epsilon 0 A by D minus T. This is for conducting slab. And dielectric slab, epsilon 0 A by D minus T plus T by epsilon R. If you don't have time and if you haven't learned this, the derivations can be skipped, but learn the equations. This is for conducting slab. This is for dielectric slab. Conducting slab, distance is D, thickness is T. Here epsilon R is dielectric constant. And coming to the last point, what was the next point? Derivation of capacitor. Epsilon 0 A by D is important. Combination based numericals, that's important. Effects of introduction of slab, I'll tell you now. Like this. Then energy equations. This time energy equation is deleted, but energy has 3 equations. Half QV, Q square by 2C, and half CV square. You got 3 equations for energy stored. And introduction of a slab. When you introduce a slab, capacitance will increase. You can have different questions on it. When battery is connected, if they say battery connected in a question, just know that charge is constant. Charge will be constant. If battery removed, that means voltage will be constant. Okay, that's all from the first 2 chapters, electric charges and fields, electric potential and capacitance. Now, Rafi sir will come with magnetic effects of current and magnetism and matter. Come on, Rafi sir, welcome. Welcome, Rafi sir.
Yes, sir. All right. Hi, good morning, everyone. Good morning, all. Good morning. Hopefully, all are in the serious preparations. Let me discuss you current electricity very quickly. Look at this important topic, drift velocity numericals. Okay, look at this drift velocity derivations and the numerical. Okay, Ohm's law, mobility, graph and slope. I will tell you what it means. First I am reading resistivity and stretching of wire. N square times R. I will show that. J is equal to sigma E. Important derivations, vector form of Ohm's law or microscopic form of Ohm's law. Then graph and temperature dependence. That means resistivity, temperature graph of all alloys, metals and semiconductor. Okay. Then KCL and KVL, very very important. The definition is important and its numerical is important. Remember MCQ question, KCL is based on law of conservation of charges, KVL is based on law of conservation of energy, which is an important MCQ question. Wheatstone bridge is another important one, easy only. If you have not learned this one, it's very easy things. Any student who are not learned this one, please immediately learn. It's an easy things only, easily to remember this one. Wheatstone bridge. Okay, Wheatstone bridge derivation, very important. Numerical. This is 3 or 4 patterns of numericals are there. Wheatstone bridge, important area, must focus that. Then cells combinations. That means cells in series, cells in parallel derivations. Okay, you want to learn that. Then internal resistance, the internal resistance of cell and its numerical. Okay, let me tell you that. Let me tell you, page number 9, right? Okay, 1 second here. These are the complete equations. Look at this. I will just quickly overview this one. Drift velocity, what's the formula? EE by m into tau. What does E stands for? Electric field. E means what? Charge of electron. M means what? Mass of electron. What is E by M called? Specific charge of electron. Remember that. Sometimes they give specific charge directly. Alright. And you guys want to remember one more thing. Electric field sometimes they will not directly give. Electric field given by voltage by length of the conductor. Remember this formula. Sometimes you will get easy numericals. Okay. That's level only board will ask. Just remember that. Then V is equal to IR. This is what we call Ohm's law. And mobility means what? Mobility. Drift velocity by electric field is called what? Mobility. And VI graph is what? This is a VI graph, and resistance will be directly the slope. Instead, if the axes are interchanged, IV graph, then resistance will be what? 1 by slope. Are you okay? Then resistance and relaxation time. Tau means what? Relaxation time. That is, electrons are colliding in between the inside the conductor. The time interval between the collision is called what? Successive collision is called relaxation time. How it depends on resistance? ML by NE square A into tau. All right. Then resistivity, what's the formula? RA by L. This derivation is important, and resistivity derivation is important. Frequently asked question. Remember this is a frequently asked derivation question. Keep in your mind. And resistance due to stretching of wire. What happens if you stretch the wire into n times the length? N square times R. Remember this option? We did one question based on the last class. N square means N means what? How many times you are stretching that? You are stretching to 3 times, then 3 square R. 4 times 4 square R. Like that MCQ you can expect. Look at this then. J is equal to sigma E. Very very important derivation. Microscopic form of Ohm's law. Then these are the resistance versus temperature graph of a metal alloy semiconductor. All right. So remember this graph. It will give you easily the score. Okay. Remember this graph. Okay. The 3 shapes. And Wheatstone bridge. What's the Wheatstone bridge? P by Q is equal to R by S. This is the balancing condition of Wheatstone bridge. You record to derive this. Okay. You record to derive this one. Learn this derivation. Yes. Then cells in numericals also you can expect. Then cells in series. The total EMF. When many cells are connected in series, how will you find the total EMF? E1 plus E2 plus etc. Resistance in series connection. R1 plus R2. What this R stands for? Internal resistance. Are you okay? Then parallel connection. How will you find when cells are in parallel? EP by RP is equal to E1 by R1. Every cells, you know, E by R, you just add, then you will get what? Total E by R. And how will you find the total internal resistance in parallel connection? This one. Okay, what's the internal resistance formula? Remember this derivation, like can be asked like a 2-mark questions. R is equal to E by V minus 1 into capital R. What this E stands for? EMF of cell. V stands for what? Terminal potential difference. Capital R means what? External resistance. Okay, this is just a quick review of the chapter current electricity. Expecting you got this. Alright, so for this time being, I'm moving very quickly. In case you need to take the screenshot, take a screenshot with me very quickly. Alright, hopefully you have done this. Let me go to the next chapter. Yes, right. Let me go to the next chapter, that is moving charges and magnetism. What are the important chapter points of moving charges and magnetism? Lorentz force and numericals. Alright, then Biot-Savart's law and vector form. Important. Sorry, I forgot to mark you. Most important thing here, the 5-star point. The 5-star point will be, I am giving the preference to this one. Okay, this is a 5-star category, must revise. These are the 5-star category, sure short question area. And cells in parallel, I mean cells in combination, cells in parallel is the most important that one. Okay, so keep that one in your mind. And this also, you just give like, you can expect like a 3-mark questions in between. Hopefully that's fine to you. Then come to the moving charges and magnetism, Lorentz force numerical. I will show the equations in quickly. Biot-Savart's law and vector form. Okay, you want to remember the vector form of Biot-Savart's law? MCQ questions can be expected from there. There is an NCERT textbook question is there. There is a straight element. You must want to practice that. Like what is the magnetic field due to this small element delta X. You can refer that NCERT. I forgot about that example number. You can refer it. Must revise that Biot-Savart's law numerical. And magnetic field to a coil. Very important. Circular coil. Axial is equal to mu 0 IR square by 2 into R square plus X square all raised to 3 by 2. Don't worry. I will show the equations. Ampere circuit law. Statement you need to learn. Statement you learn to learn. And here also statement you learn to learn. You need to learn. All kids can easily score that area. Force on a wire due to magnetic field. Then force between the conductor. Torque on a coil in a magnetic field. And moving coil galvanometer and the conversion. This is one of the 5-star category. Sure short question area. Remember this. One of the. I am recommending you. Excel team recommending you. You must learn this area. You will get 5 mark nearly from this area. Explain the working of moving coil galvanometer. What's the working principle? Circuit diagram. What is the purpose of soft iron there? What is the radial magnetic field? Concave shaped magnetic field, etc. What's the purpose of this? How to convert conversion to galvanometer to voltmeter, conversion of galvanometer to ammeter. NCERT exercise question. There is 2 questions are simple direct questions usually comes in examination. Learn that 2 questions. Okay, learn that questions. Let me show you that. Let me show that slide to you. Like moving charges and magnetism. One second. Okay, this is a moving charges and magnetism complete equation. Okay, look at this. Magnetic force on a moving charge when it is entering to the magnetic field. What's the formula? QVB sin theta. What theta stands for? Angle between velocity and magnetic field. And what this one? It is a force of charge particle when it is entering both electric and magnetic field. Look at this. Charge is moving both electric and magnetic field. What's the total force? This is what we call the this is called the Lorentz force. Okay, Lorentz force. This is individually called as what? Magnetic Lorentz force. So this is the formula. And here's one of the very famous question is there. What is the velocity required to move a charge particle undeflected way in both electric and magnetic field? The answer is V is equal to E by B. If the charge is going with E by B velocity, then charge will not experience any force, so charge will go straight way. That's very important. Keep in your mind that point. Okay. Then the Biot-Savart's law, mu 0 by 4 pi I into dl cross R by R cube. Okay. The vector form of Biot-Savart's law is a vector form of Biot-Savart's law. Biot-Savart's law you learned what is R square only denominator, but you are writing vector form. There will be R cube will be. This is a MCQ expectable point also. Yes, keep in your mind that magnetic field at the axial point of a circle mu 0 IR square divided by 2 into R square plus X square all raised to 3 by 2. Very important derivation. After moving coil galvanometer, this is the next 5-star derivation. Okay, keep in your mind. Magnetic field center of a circle mu 0 I by 2R, where R is the radius. All right, that's fine. Then this Ampere circuit law. Line integral of magnetic field over a closed loop is equal to mu 0 times current enclosed in it. That's fine. Magnetic field inside a straight wire mu 0 IR by 2 pi R square, where small r is the distance from axis to the point, capital R is the radius. Okay, out of the magnetic field. What's the magnetic field outside circle? Mu 0 I by 2 pi R. Surface of a straight wire mu 0, sorry, so everything is straight wire. Okay, mu 0 I by 2 pi R. Here it is a radius. So I hope you guys are remembering that graph. The magnetic field variation with the distance, it will be like this. It's an important derivation. Okay, this is also an important derivation. Must learn that. And force on a current carrying conductor kept in magnetic field ILB sin theta. Remember that question. When a current carrying conductor, what is the condition to keep a conductor in mid-air? That means you need to provide a magnetic field like this. Then magnetic field will be hauled this one to upward. That force is what we call the ILB. So it can balance it by weight. Then mg is equal to ILB. So this kind of questions is a very important pattern. What is the required magnetic field for keeping a conductor in mid-air? You can find the B value here. That's a very famous question. Don't forget about that. Okay, F is equal to ILB sin theta. What this one? There are 2 current carrying conductor. Very important. Parallel current carrying conductor. What's the force between them? Mu 0 I1 I2 L divided by 2 pi d. Okay, that's the formula. Or force by length is equal to this thing. Here one of the very important definition is there. Definition of 1 ampere. Very important. One more question. A, B, C. C part they will ask this one. Alright. Then torque on a current carrying conductor. What's the formula? NIAB sin theta. N stands for what? Number of turn. I means current. A means area. B means magnetic field. Theta means angle between magnetic field and area vector. Alright. Then what this one? It's a galvanometer equation. C phi is equal to NIAB. Remember this equation? What's phi means? The needle deflection. How much the needle is deflecting? C means torsional constant. N means number of turns. I means current. A means area. B means magnetic field. This is the formula for galvanometer equation. That's fine. Now, you don't forget about this one, very, very important. Galvanometer to ammeter, how will you convert? Connect a shunt resistance parallel to the galvanometer. What's the formula for shunt resistance? IgG divided by I minus Ig. What's Ig? Ig stands for current through the galvanometer to get full scale deflection. Capital G means what? Resistance of galvanometer. I minus Ig. Okay, what is I means? Total current which you require to measure the ammeter. Okay, so then what is the conversion of galvanometer to voltmeter? R is equal to V by Ig minus G. V by Ig minus G. V is the voltage which you want to measure from that voltmeter. Ig means maximum current you can give to the galvanometer to get full scale deflection. G means resistance of galvanometer. Resistance to be connected in series to make galvanometer. Hopefully remember that. Very, very important. Hey guys, if you are like little weak, this is a very important corner. Must remember that. Okay, this about moving charges and magnetism. You got it right. I am recommending here the most important derivation will be this area and circular coil. Okay, well, circular coil. Okay, circular coil. I don't have a time. So force between the parallel current carrying conductor, definition of 1 ampere. Okay, definition of 1 ampere. All right, this one is a very important. All right, hopefully you got the idea. Then let me come to the, I'm not wasting your time. That's why I'm running fast. The next one, magnets and matter. What do you want to learn from here? Small lesson only, just less weightage. Look at this, bar magnet and numerical. Means what? Bar magnet properties. Okay, what's the property of bar magnet? And axial field formula, mu 0 I 4 pi 2 m by r cube. Like you learned electric field at the axial point 1 by 4 pi epsilon 0 2 p by r cube. Na? Similarly, magnetic moment. Okay, magnetic moment is m, axial field, equatorial field. Okay, remember that. Equatorial field is axial field by 2. That's fine. Then potential energy derivation. Okay, potential energy derivation. Like how you did electric dipole potential energy derivation. Similarly, you have to do magnetic bar magnet potential energy also. Minus mb cos theta. Minus mb cos theta. All right, theta is the angle between magnetic moment and magnetic field. You guys know, right? What's the magnetic moment of a bar magnet? South to north. South to north is the magnetic moment of a bar magnet. Like electric dipole moment, minus q to plus q. After that's fine to you. Stable and unstable equilibrium. This is what stable equilibrium. A bar magnet aligned along the magnetic field. Bar magnet is, opposite, then it will be what? Unstable. Theta 180, theta 0. Diagram you want to remember. After that's fine to you. The next one, work done to rotate a dipole from one angle to another angle. mb cos theta 1 minus cos theta 2. In case you learn like this, minus m, if you are using minus mb, then reverse cos theta 2 minus cos theta. Whatever you learn, you can forward that, no issue. Okay, you don't want to correct at the last moment. This is a work done to rotate dipole from one angle to another angle. mb cos theta 1 minus cos theta 2. Theta 1 means initial angle, theta 2 means final angle. Like here, you need to rotate from this orientation to some other orientation, then theta 1 is 0. What's the record angle? That's what theta 2. Okay, you can substitute here. It's a very famous. You learned this one, right? Already electrostatics. Come on. Then it's a very, very important topic. I'm just recommending you. This is the most important topic. Paramagnetic, ferromagnetic, diamagnetic substance. Their examples is very important because the examples only they will give. You want to recognize which material is this one, identify their properties. Okay, so that things. And remember the paramagnetic and ferromagnetic, first one is what? Dia, then what? Para, then what? Ferro, right? You know their magnetic field lines pattern. So it's very important, magnetic field lines pattern. Okay, magnetic field lines pattern. So magnetic field lines are like little wide apart here, but very, very close here in para. Here it is far apart. Okay, so they will provide you this graph, this diagram, then they identify what is dia, para, ferro, etc. They will ask and list out some properties. And you can get one more question really easy. Mu r is equal to relative permeability is equal to 1 plus chi, where chi is called susceptibility. So they will provide you susceptibility something 5000. Then what's relative permittivity? That kind of short answer question only. So 5000 plus 1, that will be the relative permittivity. Okay, relative permittivity. Okay, Lijo sir, then Lijo sir will take this electromagnetic induction very shortly to you. Yes.
Hello friends, welcome back. So the next, thanks Rafisa for this. Anyway, we are moving to the next chapter, electromagnetic induction. Electromagnetic induction, Lenz's law based numericals are very important. Lenz's law based numericals. Okay, for example, I'll tell you one. Imagine like this. You have something like this. You have a ring and a magnet is falling into this. This is north pole, this is south pole. What will be the acceleration here? You know, as the magnet comes closer, north pole is coming closer. So Lenz's law states what? You know, the reason is being opposed. The reason is being opposed. The reason is approaching of bar magnet. So if north pole is to be repelled, upper face has to act as north pole. North pole means anti-clockwise direction. So what is acceleration here? Like any other body, like you and me, acceleration is acceleration due to gravity. But thanks to Lenz's law, there is another repulsion and acceleration is A. So what is the net acceleration here? It is G minus A. G minus A. That is one point. Then there are many Lenz's based numericals which you might have done already. Then motional EMF question is very important. Motional EMF. What can they ask about this? You know, motional EMF. You have a conductor which is kept in a magnetic field. Which is kept in a magnetic field like this. Alright, this is the conductor. And the conductor is moved to a new location. What will happen? Electrons will cluster at one end. That end will be negative, that end will be negative, the other end will be positive, and this will create a potential difference across the conductor, and potential difference is given by B, L, V. B is the magnetic field strength, L is the length of the conductor, V is the velocity. So they can ask what else in this? You know, they can ask the power equation. Power is given by E square by R. E square by R. B square, L square, V square by R. B square, L square, V square by R. Electrical power generated on the wire. Or they might even ask mechanical power required to pull it. Mechanical power required. Mechanical power required, why? Because as you're trying to pull, somebody is pulling you back. Who? Lenz. Lenz's law. Lenz's law pulls it back. So an external agent has to give a force. The power given, power mechanical, is same as power electrical, which is same as E square by R. They might even ask force. What is E square by R? B square, L square, V square by R. Okay, and force. What is force? Force is given by power by velocity. Power by velocity. B square, L square, V square by R by V. V and V are cut. You are getting B square, L square, V by R. This is motional EMF based question. This derivation is important. Numericals are important. And you know, another one, you know, you have a rotating conductor. This question has come 9 times across different papers in the last 12 years. You check it out. The conductor is rotated in a magnetic field. What is the EMF developed between the ends? That is given by B omega L square by 2. B omega L square by 2. Rotating conductor. For example, leaf of a fan. Okay, so when it rotates, it obviously intercepts Earth's magnetic field. Earth's magnetic field, right? Okay, so magnetic field is B. Angular velocity is omega, L is the length of the conductor. This derivation is important, B omega L square by 2. And in numerical is also important. How do they ask the question? They will give you frequency. They will say 120 RPM. How do you convert to RPS? Divide that by 60. RPM stands for revolutions per minute. Revolutions per minute, or revolutions per minute has to be converted to revolutions per second. Okay, so put it over here in omega and put it back to this equation. You will get the EMF. Remember, there is a question. A cycle wheel has spokes. Now these spokes are what? These spokes are to be taken like cells. Cells in parallel. Cells in parallel. In the case of cells in parallel combination, number of cells is irrelevant. Number of spokes is not to be counted. So in this case, in the case of cycle wheel, number of spokes won't be considered at all. There was a question to calculate the EMF, at the end of which there was another question. What happens if the number of cells is increased, number of spokes is increased? Nothing will happen. Okay, B omega L square by 2. Now the question is, Lenz's law is what? Lenz's law is law of conservation of energy. Law of conservation of energy, explain. It's very important. Look at this. This is the coil. Magnet is falling. North pole is falling. South pole is up there. Right. North pole is falling. There is repulsion. Repulsion. But even then it falls down. Why? Why? Gravity will win. Gravity will win. Gravity will overcome Lenz's force. Understood? So gravity wins. In that case, work done by gravity is converted to electrical energy. So you can say law of conservation of energy is valid here, right? Okay. Similar way, you take the magnet out. This time, how do you explain it? You are pulling it out. Okay, the coil is what? The coil is pulling it back. Why? Why? Because Lenz's law says that the cause should be opposed. So as you're trying to pull it out, somebody is pulling it back. but you will win because you are stronger, right? You will win. So work done by the external agent, that is you, will be converted to electrical energy. So either way, it is either work done by gravity or work done by the external agent that is converted to electrical energy. That is why we say Lenz's law is law of conservation of energy. There are 4 things you learn. Okay, Kirchhoff's first law, law of conservation of charge. Kirchhoff's second law, law of conservation of energy. Photoelectric effect, law of conservation of energy. Lenz's law, law of conservation of energy. That is very, 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 very important. Kirchhoff's first law, law of conservation of charge. Kirchhoff's second law, law of conservation of energy. Then Lenz's law, photoelectric effect, both are law of conservation of energy. All right, now let us go to the next one. What is the next point? What is the next point? Come on guys, come on guys. You know, motional EMF based numericals. I told you self-induction, mutual induction, numericals. You know what self-induction is? Self-induction, you know, look at this. You know, I have a coil here, I have a cell, I have a switch and a coil. What happens when you switch it on? You know, the current starts to increase. When the current increases, magnetic field will increase. When magnetic field increases, flux increases. Then let us trust Lenz. Lenz says what? Or Faraday, rather Faraday. Faraday says what? You know, flux changes and EMF is developed, right? So when you switch it off, current decreases, field decreases, flux decreases, EMF is developed. So EMF is developed whenever there is a flux change. This phenomenon is called self-induction. There are 2 equations here. Phi is equal to Li, E is equal to minus L into di by dt. They may ask numericals on this. Only direct numericals, only direct numericals. L into di by dt. Okay, L into di by dt. So this is self-induction. And self-inductance of a solenoid is a derivation here, which is very important. Self-inductance of a solenoid. Self-inductance of a solenoid is given by mu 0 n square A by L. N is the number of turns, A is the area of cross section, and L is the length of the solenoid. Mu 0 mu r n square A by L. If you insert something inside the pipe, okay, if it is air cored solenoid, it is simply mu 0. If it is iron cored solenoid, copper cored solenoid, aluminum cored solenoid, you have to put the corresponding mu r over there. Got it? So in the reader, they have done something else. They have multiplied with L. They have multiplied with L. N square by L square can be called small letter n square. Small letter n is called number density. That point is also important. Then we have mutual induction. Nothing. Self-induction is one coil. Mutual induction means 2 coils. Mutual. So you got 2 coils over here. Cell switch and second coil. This is galvanometer. First coil is primary. Second coil is secondary. What happens when you switch it on? Primary current increases. Primary current increases because cell is in primary. So primary field increases. Primary flux increases. Similar way, when switched off, you know, primary current decreases, primary field decreases, primary flux decreases. You know, this will cause secondary flux to change and EMF is developed. That EMF is called mutual induction. What are the equations here? Phi S is equal to, in place of Li, phi S is equal to MIP, and EMF, ES is equal to minus M into DIP by dt, right? So that is mutual induction. You can expect a direct numerical on this. And mutual inductance of a pair of coaxial solenoids. It is mu 0, mu r, ns, np, a by L. The only difference between these two is here it is n square, here it is nsnp, here it is n square, here it is nsnp. Once in last 10 years they asked this also. It is not explicitly mentioned in the reader. Mutual inductance of a pair of coils. Check it out if you have time. Mutual inductance of a pair of coils. It is derived the same way. Mutual inductance of a pair of coaxial solenoids. Okay. And motional EMF we did. Energy stored in an inductor. Only the equation matters. Energy stored in an inductor is half Li square. It is magnetic in nature. And this year we expect a case study question to come from either transformer or diffraction. Transformer, generator or diffraction. Case study question to come from transformer, diffraction and generator. Okay, transformer, you know, working principle is mutual induction. DC can be used in a transformer. For converting DC, transformer. For changing the value of DC, transformer cannot be used. And transmission is done how? Power transmission is done at low voltage, high current. Options will be given. Power distribution will be done at high voltage, high current, high voltage, low current, low voltage, low current, low voltage, high current. Power distribution is always done at low voltage, high current. Hear me again, low voltage, high current, low voltage, high current. That is to reduce the transmission losses. Transmission losses. There are two types of transformers, step up and step down. Both are important. Learn the energy losses also. In a transformer, there are energy losses like flux leakage loss, copper loss, eddy current loss, iron loss, humming loss. There are different losses. They'll ask to name the losses. Name the losses. Not in detail. Name the losses. That's it. Okay. And I would say this is the most important question this year. You know, like Rafi has said, you know, this important question here is motional EMF due to rotating conductor, motional EMF due to rotating conductor, or motional EMF due to a straight conductor. That is important. Okay, we will move to next one. Alternating current. Alternating current generator, I already told you. AC generator. The principle is very important. Principle is what? Principle is electromagnetic induction. Again, AC generator, somewhere in the reservoir, and Niagara Falls, somewhere in the reservoir you store the water. Water falls on a turbine. Turbine rotates. Automatically electricity is generated. Same AC generator you learn in class 10. You know, the graph is important. The parts are armature coil, field magnet, slip rings, graphite brushes. Armature coil, field magnets, slip rings, graphite brushes. Okay, and working and derivation. This derivation is equal to minus d phi by dt. You start off from Faraday's law, then put phi value as NAB cos theta. In the end, you get E0 sin omega t. That is what you do. Then, you know, general form of AC. General form of AC I already wrote. is equal to E0 sin omega t. is equal to E0 sin omega t. Then LCR circuits, resonance, quality factor, power, wattless current. I'll do them now. Look at this. You know, general form of AC is what? General form of AC is E0 sin omega t. Current is what? I0 sin omega t. This E is called instantaneous voltage. E0 is called maximum voltage or peak voltage or amplitude. Maximum voltage or peak voltage or amplitude. Omega is called angular frequency. Angular frequency. Current is given by I0 sin omega t. Right. I is instantaneous. I0 is peak. What is average value? Average value is given by 2 by pi times E0. That is 0.637 E0. Remember, this is average over positive half cycle only. What about negative half cycle? That is minus 2 by pi E0. Here comes an important question. What is average over full cycle? It's 0. Never ever forget it. Average value of AC over a complete cycle is 0. Average value of AC over a complete cycle is 0. Average value of EMF over a complete cycle is 0. Average value of current over a complete cycle is 0. Then we define a new value called RMS value. E0 by root 2. That is equal to 0.707 E0. Expect a numerical from this side. Direct one based on this general formula. And remember, RMS value in a numerical, in a question paper, the current value, voltage value given is always RMS value unless mentioned otherwise. Usually what is given is a measured value. Measured values are always RMS values. So in the question if you see 230 volts, it's RMS value. In the question if you see 17 amperes, that is RMS value. Got it? So keep that point in mind. Second part is about circuits. Second part is about circuits. Okay, we have purely resistive, purely inductive, purely capacitive, then combination LCR, LR, CR. LC is not there anymore. LC is deleted. LC is deleted. Purely resistive circuit, voltage and current are in phase. Phase difference is 0. Purely inductive circuit, phase difference is pi by 2. Purely capacitive circuit, phase difference is pi by 2. Purely inductive is pi by 2. Purely capacitive is pi by 2. You can memorize it this way. Li the Iceman. Li the Iceman. Look at this. Li the Iceman. L stands for inductor. In inductor, which letter comes first? EMF. So EMF is leading, current is lagging. Current is lagging. In capacitor, current is leading, EMF is lagging. Li the Iceman. Okay, anyway, the phase difference difference is pi by 2. Okay, this is purely resistive, purely inductive, purely capacitive. For purely inductive and capacitive, derivations are important. Show that the phase difference is pi by 2 in a purely inductive. Show that the phase difference is pi by 2 in a purely capacitive. Actually, there are 3 derivations only in this chapter. One is show that phase difference is pi by 2. Show that phase difference is pi by 2. Third one is the derivation for power. Okay, now the combined one is LCR circuit, inductor, capacitor, resistor circuit. Okay, this is called LCR circuit. You must know how to draw the phasor diagram. Current is drawn here, VR is drawn here, VL is drawn here, VC is drawn here, VL minus VC drawn here. Complete the parallelogram, draw the diagonal. This is V, this is phi. And you have to take tan phi and cos phi. How? Impedance triangle. On the base resistance, on the altitude reactance. Automatically hypotenuse will be impedance. Take this as phi. You have to find cos phi. Why cos phi? Cos phi is called power factor. Which will come in handy later on when we do the numericals. Power factor. Also tan phi you have to know. This year I expect a question here. Tan phi is opposite side by adjacent side. XL minus XC by R. What if I multiply throughout with IXL, which is VL, minus IXC, which is VC. I into X is volt, right? Voltage. IXL minus IXC divided by IR, which is VR. They will give you XL, XC, R. They will ask you to find phi. They will give you VL, VC, VR. They will ask you to find phi. Okay. And that's all about LCR circuit. Then 2 more points to go. I'll tell you resonance. 1 point is resonance. I'll tell you before that, XL against frequency graph is important. XL is L omega, right? So they might ask you to draw XL against omega. And the graph will be a direct proportionality, right? And what is the slope of the graph? Slope of the graph is XL by omega. Y-axis by x-axis. I've told you 100,000 times. Tell me what is slope of the graph? Y-axis divided by x-axis. Y-axis by x-axis. Y-axis by x-axis. So this comes to left side. What is it? XL divided by omega will be what? L. So slope of this graph represents what? Inductance. They will give you 2 graphs. They will ask you to find the ratio of inductances. They will give you this angle as 30. They will give you this angle as 60. Right, so you can take tan 30 to tan 60 ratio. That will give you self-inductance. What about capacitive reactance? That graph is also important. Xc is equal to 1 by C omega, 1 by C into 2 pi F. Look at the proportionality, inverse proportionality. Xc against F is this graph. Okay, inverse proportionality graph. Okay, that's also important. The graphs are important. Now here we come to the last part of this. The resonance in LCR circuit. Anything else is left? Resonance, quality factor, power, wattless current. Yes. Okay, that will be done in 2 minutes. Resonance is a particular condition. You take an LCR circuit, inductor, capacitor, resistor. Okay, LCR circuit. You feed a particular frequency. What is that frequency? 1 by 2 pi root of LC. You can give the frequency you want. L is the inductor value, C is the capacitor value, and R is the resistance. You put the frequency, and what are you going to get? You will get a lot of conditions. 11 conditions you can write. They are all from previous papers. Inductive reactance equal to capacitive reactance, and Z becomes equal to R. Circuit is purely resistive now. Now phase difference will be 0. In that case, cos phi will be 1. Voltage across inductor will be voltage across capacitor. Applied voltage will be equal to voltage across resistor. All these conditions are important. Power factor is 1. Cos phi is 1 for LCR circuit only at resonance. Okay, power factor is 1 only at resonance. And in the circuit you learn something called quality factor because this is used as a tuner circuit in radio, okay, or television. There we learn the quality factor. Just know the equation. This year they haven't mentioned it, but anyway, you have to expect one question because it's been repeated so many times. Nothing, they'll give you L value, C value, R value. You just have to substitute and find this quantity. That is dimensionless quantity. Okay, that's all about LCR resonance. Then there is a graph. You just draw the graph as well. The graph, frequency against current graph or frequency against power graph. This frequency is called resonant frequency. Okay, right. Okay, that is the next point. And the last part here is what? Last part here is what? So that's all about resonance. Last part is power, wattless current. That is easy. That is easy. Power, wattless current. Power is given by what? The derivation is important. Power is E0 by root 2, I0 by root 2 into cos phi. This derivation is important. ERMS into IRMS. This is ERMS. This is IRMS. Cos phi is called power factor. Okay. If it is purely resistive, put phi 0. If it is purely inductive, put pi by 2. If it is purely capacitive, pi by 2. So for L and capacitor, phi is equal to pi by 2. Put phi is equal to pi by 2, power will be 0. That means no heat dissipation. You know, you have a statement like this, an ideal inductor or capacitor never gets heated up. If it is ideal, you can touch and understand. Why? It won't produce heat. Okay, that can come in an assertion reason question. Assertion, an ideal inductor or capacitor never gets heated up. That's true. Reason, in an ideal inductor or capacitor, phase difference is pi by 2. That's also true. Check what the option is. Okay, that's an important question. And the last one is wattless current. Wattless current is given by IRMS sin phi. You know, this question has been asked in a numerical only once in last 12 years. That was a difficult question. You know, IRMS was given, but sin phi was not given. So there you had to draw this triangle. This value was given VR, VL, VC. Now this value will be phi. You can find sin phi from this. Sin phi from this and put it over here. You will get the wattless current. Wattless current is also called idle current. That's all about alternating current. Is this clear, everyone? Can I have a response, please, everyone? Can I have a response, please, all of you? Everyone, please. I'll move to electromagnetic waves. Next one is electromagnetic waves. It's simple one. Okay, electromagnetic waves. Okay, right. So electromagnetic waves, concept of displacement current. Only 3 mark weightage. If a 3 mark question comes, it's going to be this one, 100% sure. Concept of displacement current. Epsilon 0 d phi by dt. You have to write a brief note and then explain what displacement current is. Epsilon 0 d phi by dt. Another one is properties of electromagnetic wave. There is something called electromagnetic spectrum. Okay, you know, to which certain wavelengths are belonging. You know, anyway, all of them have a common property, few common properties. All of them travel at 3 into 10 raised to 8 meter per second. All electromagnetic waves travel at 3 into 10 raised to 8 meter per second. All of them do not need a medium to travel. If I remove all the air from my room, you won't be able to hear me because sound would need a medium to travel, but you could still see me. Why? Because light does not need a medium to travel. Okay, so that is second property. Then all can be polarized. Polarization is possible with electromagnetic waves. Anyway, that's another one. Frequency applications. Applications are important. Frequency ranges are important. You know, that is given in the reader in a box. That is direct. Very, very important. 100% sure. Like Rafi sir said, this is like a 5-star question. You know, you have to expect this time. Frequency applications. If you decide to skip this chapter, learn this at least. And Maxwell's equations. Who are Maxwell's equations? I'll just write down Maxwell's equation. First one, integral E dot ds is equal to 1 by epsilon 0 into q. This is called Gauss's law in electrostatics. Integral B dot ds equal to 0. This is called Gauss's law in magnetism. Integral E dot dl is equal to minus d phi by dt. D phi b by dt. This is called Faraday's law of electromagnetic induction. And the last one, modified Ampere's circuital theorem or generalized form of Ampere's circuital theorem. It is integral B dot dl is equal to mu 0 into IC plus ID. IC is called conduction current, ID is called displacement current. Displacement current is given by epsilon 0 d phi by dt. How do they ask the question? They will ask you to write the 4 Maxwell's equations. These are the equations based on which electromagnetic theory is built. Okay, this is the foundation stone for electromagnetic wave theory. Then electromagnetic spectrum. You know, you can memorize the electromagnetic spectrum this way. Raging Martians invaded Venus using X-ray guns. Raging Martians invaded Venus using X-ray guns. This is radio wave, microwave, infrared, visible. Visible is violet, indigo, blue, green, yellow, orange, red. Okay, violet, indigo, blue, green, yellow, orange, red, Vibgyor. Then ultraviolet, X-rays, gamma rays. Now all of them belong to electromagnetic spectrum. So all of them constitute electromagnetic spectrum. Raging Martians invaded Venus using X-ray guns. Okay, so what is the wavelength range? Wavelength decreases as you come down. Okay, wavelength decreases. Infrared, then visible, then ultraviolet. Wavelength decrease as you come down, or frequency increase as you come down. And know this equation: E0 is equal to C times B0. Electric field is equal to C times B0. Based on that, they can ask a question. B0 is magnetic field's amplitude. E0 is electric field's amplitude. And last equation here, electromagnetic waves equation. EY, electric field may be written as E0 sine kx minus omega t, and magnetic field is written as B0 sine kx minus omega t. Here x is the direction of propagation, direction in which the electromagnetic wave is going, direction in which the electromagnetic wave is going, x. Now electric field must be what? Either on y or z. Then the magnetic field will be on y or z. They must be perpendicular. So in short, electric field, magnetic field and propagation vector must be perpendicular to each other. And remember, k value is called 2 pi by lambda, propagation constant. K is called 2 pi by lambda or propagation constant. And one last question. Static charge produces electric field. Hear me again. Static charge produces electric field. Electrostatics. Electrostatics. We learned electric field. What was the name of the fourth chapter? Moving charges and magnetism. Moving charges. So moving charge produces magnetic field. Accelerated charge produces electromagnetic waves. Accelerated charge produces electromagnetic waves. So static charge produces electric field. Moving charge produces magnetic field. And accelerated charge produces electromagnetic waves. That is all from electromagnetic waves. Rafi sir will start ray optics now.
Sir, you can also V equal to E cross B, right?
Yeah, V is equal to E cross B. This is also taken. E is electric field, B is the magnetic field. So
C equal to 1 by root of that one also.
That is also, yeah. N is equal to, you can have two more equations here. One is C is equal to 1 by root of mu 0 epsilon 0. This is velocity of light, and refractive index is given by root of mu r epsilon r. Refractive index is given by N is equal to C upon V. So if you put this over here, you will get root of mu r epsilon r. Mu 0 epsilon 0. Mu 0 is permeability of free space. Epsilon 0 is permittivity of free space. And they might ask you to derive this. All right. Or derive this. All right, that's a small derivation, nothing. You take mu 0. Mu 0 is 4 pi into 10 raised to minus 7.
You can show that then.
Yeah, I'll just show it. Mu 0 is 4 pi into 10 raised to minus 7, you know, and then 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. Then epsilon 0 will be 1 by, epsilon 0 goes here, that comes here. 1 by 4 pi into 9 into 10 raised to 9. So if you multiply mu 0 into epsilon 0, what do I get? 4 pi into 10 power minus 7 into 1 by 4 pi into 9 into 10 raised to 9. So 4 pi cut, you get 1 by 9 into, then 10 raised to minus 7 goes to denominator, 10 raised to 7,
16.
10 raised to 16. Yes. That is 1 by, this is c square.
16.
Velocity, yes. This is 10 raised to 16. All right. This is actually 3 into 10 to the power 8 the whole square. So you get mu 0 epsilon 0 is equal to 1 by c square, or c will be 1 by cross multiply. C square will be 1 by mu 0 epsilon 0. C is 1 by root of mu 0 epsilon 0. And you know, text us on this number in the comment box if you want to know how to do this root of mu r epsilon r, or try it yourself. Refractive index is given by root of mu r into epsilon r. Now Rafi sir will do ray optics.
If I miss any points, or you have to...
Yeah, sure.
Okay, yeah. Yes, all. So let me discuss ray optics then. Okay, first I think, no, sir?
Yeah.
Okay, ray optics, okay? Listen to this, ray optics. So see all, in ray optics, derivations I will tell you, I have a slide over there that I will show there. TIR, okay, it's very important, total internal reflection. The phenomenon, how do you define total internal reflection? What is the condition for TIR? What's the condition for TIR? What's the definition of TIR? When the angle of incidence in denser medium is greater than the critical angle of the medium, then complete light ray bounces back to the same medium. That's what we call the total internal reflection. You want to learn statement, and what's the condition for TIR? Angle of incidence should be greater than the critical angle, and light should travels from denser to rarer medium. Don't forget, very cute, one more question, don't forget. Then numerical, TIR numerical, TIR based numerical, this kind of questions you saw, right? When a light comes like this, what happened after incident over here? It will TIR happen, such a question. It will emerge out or reflect back. That kind of questions are very famous in TIR. Okay, and one more easy numerical question will be TIR, this one. Don't forget about this. N is equal to 1 by sin C. They will provide the critical angle, okay, like 45 degree. Then what's the N value? If suppose the critical angle is 45 degree, what is the refractive index then? Root 2, right? If you substitute that, you will get its root 2. So then asking what? Velocity of light in the medium. What's the velocity of light in the medium? C by N. What's the value? C. 3 into 10 raised to 8 by the refractive index, root 2. Okay, 1 by root 2 is how much? 0.707, because you learned in AC that. So 3 into 0.707 means it comes to be 2.1 into 10 raised to 8. It's a direct, I'm remembering one of the previous year question. It's a previous year question, okay? Remember that. So critical angle they will provide, then you can find refractive index. From refractive index you can find what? The speed of light. Weightage chapter, okay? Weightage chapter, focus well. I will show you the derivations, just wait. Then prism based numerical. Prism derivation is one of the very important and it's numerical. Okay, prism based numerical, I will show that. Lenses and numericals. Okay, lenses like you saw light now. Whenever lenses combine like this combination L1, L2, lenses combine, an object is kept in front of the lens number 1, then where will be the final image will form? That kind of questions. Okay, apply the lens formula for the first lens, then you will get what? Image of the first lens. Then that image is act like the object of next, and you can find again applying lens formula, you will get what? The final image positions. That's a very famous question. Remember that. Okay, lens numerical. Then microscope and telescope. Yes. If we are Excel team give like a 5-star category, we are this time we are providing, you know, this is very sure, na Rafizar, you don't want to say this one. We know this, na. Okay, it's a 5-star category question. It's a microscope and telescope is, you know, one of the important 5-mark question you can expect. The ray diagram you have to draw and magnifying power formula and symbol numerical like M is equal to FO by FE, they will provide you. All equations I listed here, I will show you. Just wait, relax. Okay, then advantage of reflecting telescope. There is a reflecting telescope is there, that is Cassegrain designed telescope, reflecting telescope using by mirror. And what is the advantage of that one? It is free from chromatic aberration, it is free from spherical aberration. At least remember that 2 words. It's free from chromatic aberration, free from spherical aberration. Okay, remember that word. Then mirror based question, mirror formula based question. 1 by F is equal to 1 by V minus 1 by F is equal to 1 by V plus 1 by U. Mirror formula, image distance, object distance, focal length. I hope you guys know this how to do, right? It's just a 10 standard questions. Okay, that questions. Now let me show you the respective questions, respective equations. Slide number 14. Okay, sorry. Here, no? Yes. In chapter ray optics, you can see the lens formula. What's the lens formula? Lens formula, you know, look at this. 1 by F is equal to 1 by V minus 1 by U. V is the image distance, F is the focal length, U is the object distance. Remember this. I hope you know this. And one more thing I want to add here. What is the magnification formula for lens? Magnification formula for lens is V by U. Image distance divided by object distance. Common, everyone have magnification formula is what? Hi by Ho is there. Hi by Ho. Height of the image by height of the object. Hi kids by Ho. Okay, hi by Ho. Magnification formula. Remember that. And mirror formula is what? Mirror formula, just, you know, lens is like 1 by F is equal to 1 by V minus 1 by U. Mirror formula 1 by F is equal to 1 by V plus 1 by U. That's a mirror formula. And in case of a mirror magnification, remember, mirror magnification is minus V by U. Here it is plus V by U. Here it is minus V by U. Keep in your mind that. And prism formula, this is the derivation I told you, know, very important derivation. Another important, most repeated derivation from the ray optics is, you know, that's the prism derivations, prism formula. And you want to learn the ray diagram and remember this derivation. N equal to sin A plus D by 2 divided by sin A by 2. What is A stands for? Angle of prism. What is D stands for? Angle of minimum deviation. Okay, angle of minimum deviation. And here lies a point. That's a theory question. What is the condition for minimum angle of deviation? What's the condition for, or what the prism will show you during minimum angle of deviation? The refracted ray parallel to the base of the prism and incident ray and emergent ray are form symmetry. Incident ray and emergent ray are form symmetry, and refracted ray, you know, refracted ray parallel to the base of prism. Hopefully remember, this is a prism. When during the minimum angle of deviation, refracted ray comes what? Parallel to the base of prism, and incident ray and emergent ray forms what? Symmetry. Okay, symmetry. Keep in your mind that point. Okay, like condition of TIR, condition of minimum angle of deviation, usually asking 1 mark theoretical question. And another important one, lens maker's formula. Lens maker's formula. 1 by f is equal to another 5-star category question. 5-star category question. Rapid test more important. You have to focus easy derivation only. No integration, no differences, simple geometric derivation. All kid can do this very easily. 1 by f is equal to n minus 1 into 1 by r1 minus 1 by r2. So n means what? Refractive index of the lens. R1 and R2 means what? R1 and R2 means, look at this, there's a lens. The incident, light incidenting phase radius, that's what R1. Light refracting phase radius is what? R2. Remember, if a lens like this, the curve is, the curve is facing to the right side, then you take R is positive. If the curve is facing to the left side, like in a convex, my right hand is facing to the right side, so positive radius, and this one, facing left side, so radius is negative. Be careful, okay? And remember, radius of the plane surface, like a plano-convex lens is very famous. Plano-convex lens. What's the radius of the plano-concave? This one. Plane side radius how much? Infinity. Remember those all points. And you guys want to remember, along with the derivation, the sign convention you have to learn, because that also they will ask. Write the sign convention and derive the lens maker's formula and write its assumptions. Okay, assumptions also important. Like small assumptions are there, you can refer it. Okay, just 1 mark point. 1 mark assumption and 1 mark for the sign convention, 1 mark for the lens maker's formula derivation. Okay, one for assumption, 1 for sign, 3 mark for this derivation. Total 5 mark expectable corner. Remember. All right, and this one is what? Curved surface formula. Like I actually you can verify that we done one question in our live discussion. Hopefully I remember, it's a previous year CBSE board question. An object is placed here, then a person looking from this side, okay, object is here. It's a curved surface formula application based question where the image will be formed. Okay, where will be the image formed? They have given this object distance, so here it is a curved surface, where the light is going from here, rarer to denser. So rarer to denser situation and denser to rarer situations, the formula, curved surface formula, what is this one? N2 by V minus N1 by U is equal to N2 minus N1 by R. So by heart this formula, whenever a curved surface formula refraction happen, then you can find the image distance by using this result. And N2 stands means what? N2 means refractive index of the spherical surface. N1 means where that spherical surface surrounded by. Okay, N1 is the surrounding medium refractive index. R is the radius of that surface. I told if the radius is facing to the right side, then it is a positive, left side it is negative. Okay, so when it is a denser to rarer situation, then it will be N1 and N2. You just interchange the places. Okay, N2 N1 place, write N1, N2 N1 place, you should write N2, like that. That's only the change. Then optical instrument, just aware of the formula, you will get direct substitution type questions. Simple microscope, during LDDV setting, there are 2 settings for every instrument, right? We can view the object like the object is very nearer, object is very far. Okay, in microscope while looking time, you can make the images very close to the eye, very far from your eye. So there are 2 types of settings are there for instrument. That is, one is called what? LDDV setting or stress division. What is that LDDV? Least distance of distinct division setting. What's the formula for it? Simple microscope, 1 plus D by F. What's the D? For a normal person, it is 25 centimeter. Focal length they will provide, just a substitute. Example, D is 25, focal length is 5, then 25 by 5 plus 1, 6. So magnification will be 6, like that question. And when you use this formula, when normal vision, that is relaxed vision, image is formed infinity from your eye, those case only D by F. Okay, D values for normal eye, they will not provide sometimes in the question. You guys want to remember, it is 25 centimeter. Alright, that's all about the simple microscope. Then compound microscope, remember the formula of compound microscope, magnification minus VO by UO into 1 plus D by FE. What this one? VO stands for image distance of objective. UO means what? Object distance of objective. So 1 plus D by FE. FE stands for focal length of eyepiece. And this is accurate formula, approximate formula is this one. Okay, that is minus L by FO into 1 plus D by FE. So you can use this approximate formula, mainly that kind of question only will come direct. L means what? L means the distance between objective and eyepiece. L means the distance between objective and eyepiece. How to find that objective and the distance, eyepiece distance in a compound microscope? VO magnitude plus UE magnitude. VO means what? Image distance of objective, and UE means what? Object distance of eyepiece. Okay, object distance of magnitude. Once again repeating, magnitude. UE value you will get what? Negative sign, but ignore the negative. You are finding the distance, so take the magnitude and add. Okay, that's what the tube length here. Then the another case where this is normal vision case. Okay, normal vision. If suppose in compound microscope image is formed to final infinity, then formula minus VO by UO D by FE. One will not be there. Okay, so the same thing. Then come to the telescope case. What's telescope case? Many times is repeated, okay? This is many times repeated. Remember the derivation and ray diagram and numerical point of view I'm talking. Magnification of a telescope for a normal vision, f4 by fe. What is f4? Stands for focal length of objective. fe means what? Focal length of eyepiece. L stands for what? Tube length. Tube length. That is the distance between objective and eyepiece. What's the formula? f4 plus fe. What type of question? I would like to remind you one question from there. You see here. So see, the telescope case, they're providing actually the magnification is like, 1 second. They provide f4. f4 will be somewhat, we can say it is 20, and fe they given like something like 10. Okay, imagine 10. Then they were asking what's the tube length. What's tube length here? You know, right? f4 plus fe. That is how much? 30. That kind of questions. Then magnification. How will you find f4 by fe? All kids can do this. Don't leave it. Okay. Don't miss this question. Don't miss this question. Keep in your mind that. All right. So yeah. And in case of a telescope under LTDV setting, formula f4 by fe 1 plus fe by d. And what's the tube length in that particular case? Remember, it's a normal vision tube length formula. f4 plus magnitude of ue. Magnitude of ue. Remember, it's very important. Okay, sir. Is any other additional point? You can.
That question,
yes, sir.
That what is the area through which a circular area through which,
yes, sir.
That question also.
Yeah, you can do, sir. You can.
Yeah, the circular area through which a fish under water can see the outside world. Okay, it is given by, this is important, the area through which, circular area through which a fish underwater can see the outside world. Yeah. It is given by d by root of n square minus 1. Radius is given by d by root of n square minus 1, where d is the depth, n is the refractive index. Or another one, imagine a bulb is kept here. What is the area through which light is coming out? Area which light is coming out. This can be asked as a derivation. R is equal to d by root of n square minus 1. Okay. Or they will give the values, d value, n value. You can find the radius. If you find the radius, area will be what? Pi r square. Yes. Pi r square. Okay.
In case that's of d is also h, right?
Yeah. D is given as h.
You can follow that.
Yeah. It is important. Okay. So radius of the circular area through which light is coming out, or radius of circular area through which a fish underwater sees the outside world.
Sir, once again we can give optics very important. Once again we can give what are the important derivations here. Once again, last moment to students.
Prism. As you said, formula. Prism is the most important one. Lens makers formula.
And assumptions and sign also, right?
Yeah.
Then microscope or telescope.
Then total internal reflection conditions. Base numericals also.
Numericals. Yeah. Okay, sir.
Thank you, Rafi sir.
Then sir will continue.
Yeah. I'll take. Okay now. Okay. Technical team?
Yeah.
Right.
Correct.
Okay, so moving to the next one, this is wave optics. Now we are done with ray optics, and Rafi sir has covered every single point from ray optics. Okay, and this is wave optics. Wave optics, they can ask these questions. Huygens principle of secondary wavelets. Point number one, that can come as a standalone 3-mark question. What are the tenets of Huygens principle? What are the points of Huygens principle? Number one, every source of light acts as a center of disturbance. Every source of light can act as a center of disturbance from which light waves are emitted in all directions. Number two, on any wavefront, every point can act as source of fresh disturbances. Source of fresh disturbances called secondary wavelets. Third point, an envelope to these secondary wavelets gives the position of new wavefront. Also know that on a wavefront, phase difference between particles is 0. That's a previous MCQ. On a wavefront, phase difference between particles is 0. Right. So Huygens principle based questions. Law of reflection and law of refraction. Very, very, very important 3-mark questions. This time no derivation in this topic, so you have to expect this question. Law of reflection. Prove law of reflection and law of refraction. I is equal to R. This is called law of reflection, right? And law of refraction, sin I by sin R is equal to N2 by N1, otherwise called Snell's law. Both can be proved based on wave theory. That is also very, very important, based on wave theory. Then Young's double slit experiment based numericals. In the last live session, we did all types of YDSE numericals. If you haven't watched it, take time to watch it. That'll be worth it. Okay, because you'll get all numericals, YDSE numericals, particularly Young's modulus, Young's Experiment width of the band is given by lambda d by d, and underwater it is beta dash equal to beta by n. Then there are many things like angular fringe width. Then what is the distance to the nth bright band, nth dark band, and all those things. And then there is an important point, condition for maximum and minimum. In interference, the condition for maximum is path difference is equal to n lambda. Condition for interference maximum is path difference equal to n lambda. Condition for minimum is path difference equal to n lambda is condition for maximum. Path difference equal to 2n minus 1 into lambda by 2 is the condition for minimum. Here n has to be started at 0. 0th band. Central band is always a maximum. Why? That is another important question. I expect that question this year. Excel team suggests this question because it's so important. It has come so many times. Why is a central band always a maximum? Because the paths are identical. Path difference is 0. Phase difference is 0. Central band will be a maximum. Alright. Then minimum. Remember, your teacher might have given 2n plus 1, but it is safer to take 2n minus 1. You can start n at 1. If you are going by your teacher's way, you have to put 2n plus 1 and start with n equal to 0. But you better take 2n minus 1 and put n is equal to 1. First dark band is n is 1. Okay. Then we have, other questions, paths. In interference is simply a redistribution of energy, or interference is law of conservation of energy. That is a very, 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 very important question. Trust me, guys, you're going to see that question tomorrow. Interference is simply a redistribution of energy, or law of conservation of energy. In the dark band, energy is not gone anywhere. You look at that energy look for that energy where in the bright band's energy has increased now. So you can mathematically prove it, which you might have already done. Show that in interference, energy is not destroyed, energy is not created either. So it is law of conservation of energy. Diffraction based, we already told you. We expect from Team Excel, we expect only case study questions this year, numericals. Condition for maxima, minima, you have to know, they are just getting reversed. d sine theta, path difference. In diffraction, the condition for maximum is d sine theta is equal to 2n plus 1 into lambda by 2. You start n with 1. And condition for minimum is d sine theta is equal to n lambda. Alright, D is slit width. See, you have single slit only, single slit. And comparison of interference and diffraction. And the most important comparison is this, intensity variation. In interference, all the bright bands have equal brightness, or all the dark bands have equal darkness. Look at the height of the graph. Look at the height of the graph. All the graphs have same height. All the graphs have same height, right? Which means all bright bands will be of equal brightness in interference. But in diffraction, it is not so. The central band is brightest. And as you go outwards, the brightness keeps decreasing. The brightness keeps decreasing. On y-axis, you plot I. On x-axis you plot path difference or phase difference for that matter, because path difference and phase difference are directly proportional. Then drawing different types of wavefronts, that's another important question. Different types of wavefront. You might have done this, if you have a convex lens, how do you take the wavefront? This is the wavefront, plane wavefront. Now this secondary wavelet travels least inside, most outside. Then this secondary wavelet travels most inside, least outside. This secondary wavelet travels from every point, right? This is the incident wavefront. And this one travels least inside, so most outside. You connect them, you get what? You get a converging wavefront. They can ask this for convex lens, concave lens, convex mirror, concave mirror, prism. Prism I'll do, this is what prism is. Look at this, this is the incident wavefront. I'm taking 3 points. Who is traveling the most inside? Most inside is C, so least outside is C. Now B travels little more inside, little less inside, so little more outside. A travels, secondary wavelet from A travel least inside, most outside. Connect them. This is my refracted wavefront that is consistent with ray optics. No problem with ray optics. Look at the ray. you know, the incident ray bends towards the normal, right? That is what Rafizar just said, right? Prism, derivations also he said it is important. Okay, so this is converging wavefront. They might ask this as example for converging wavefront or diverging wavefront. This is converging wavefront. If you take a concave lens, you will have a diverging wavefront like this, diverging wavefront like this. Okay, you can check reader for this. Converging wavefront, diverging wavefront, convex mirror, convex lens, concave lens, and prism. That's all about wave optics. I hope I have covered every point. And the most important, since derivation is not there this time, by all chances, a case study question from diffraction you can expect, or Huygens principle, law of refraction. And numerical comes, it's going to be 100% YDSE, Young's double slit experiment. And
yes, sir, you can give a 3-star to this, no?
Yeah, this is 3-star question. Yeah, right.
Yeah.
Thanks for that.
And
right.
so this compare students can remember.
You know, this is also
area.
that is also important area, because comparison also can come for 2 or 3 marks. Thank you very much, sir.
That's great.
Yeah, that's it.
You're done all.
Next is dual nature, right? Next is dual nature. So let me take pleasure in introducing our new faculty, Mr. Anas, and he has been teaching for 10 years and he's really expert. He's really an expert in the field of physics. So let us introduce Anas sir. He'll be taking dual nature.
Thank you. Yeah.
Thank you, sir.
Next, sir.
Evan.
Yeah.
And we don't have much time to spare, so I'm going directly into this chapter. This chapter is the 11th chapter. That's dual nature of matter, dual nature of particle and radiation. Let's look at what are the main topics, what are the main points you have to be remembered. That is, the first one is de Broglie wavelength. Right? De Broglie wavelength. De Broglie wavelength is very important, and I have another slide here. That is.
Okay, sir.
3. Okay.
Yeah, 3, sir.
Now, please look at this. This is de Broglie wavelength. You have an equation for de Broglie wavelength here, that is lambda. Lambda is actually wavelength of matter wave. Matter wave was first proposed by de Broglie, and the equation for lambda is equal to h by mv. And for the numericals, you can use this equation, that is h divided by root of 2m kinetic energy, or the kinetic energy can also be written as qv. Or in the case of an electron, that Q can be written as E. Then the equation for lambda will be h by root of 2m eV. Now, the next point will be the photoelectric effect. The photoelectric effect is a very important part. Through the photoelectric effect, through the idea of photoelectric effect, we can understand the dual nature of light. In the previous chapter, we just learned that light is a wave. So light has a wave nature. In this chapter, through these ideas of photoelectric effect, we are going to learn light is not just a wave, it has a particle nature also. For that, there was an experiment of Halvash and Leonard. Halvash and Leonard did an experiment, and through that experiment we can find so many properties of photoelectric effect. There are some important graphs. The first graph is, this is the current, this is the photoelectric current. So before that, let me just introduce you to the photoelectric effect. That is, when light is coming into this metal surface, this metal surface has a property. Due to that property, that metal surface can emit electrons from it. That is called photoelectric effect. Right? Now, there is a graph. That graph is between photoelectric current. That is, this electron can be called photoelectron. Now, due to the flow of that electron, we can get a current, that is photocurrent, and this is a graph between photocurrent versus intensity. This is directly proportional. When intensity of light ray increases, photoelectric current also increases. This is the first graph, very important. You can expect questions from this graph. And the second graph is potential. voltage versus photoelectric current. That is this graph. Here in the x-axis you can see accelerating anode potential, and for the negative x-axis you can see retarding anode potential, and for the y-axis you can represent photoelectric current. Now the graph will be like this, and if the accelerating anode potential increases, you can have a value of current. That value of current will soon reach a saturation value. This is called a saturation current. This is a saturation current. This is the maximum current that can be possible from here. Beyond this, there is no current, there is no increase in current. And if we are applying a negative potential, that current can be reduced and finally come to the value V0. That can be called stopping potential, right? And if we are increasing the intensities, this is the first intensity I1, and if we are increasing the intensity, that is I2, you can have a larger value for saturation current, that is shown in this graph. And if we are increasing further, intensity is increased further, then you can have more saturation current, more value of saturation current. But you have to remember, the stopping potential will not be changing if you are changing the intensity. Intensity does not depend on saturation, intensity does not depend on the stopping potential. Okay, now the third graph is between frequency and photoelectric current. This is photoelectric current, like always, is represented in the y-axis, and the voltage is represented in the x-axis. And in this graph is very important. You can see that the value of saturation current is a constant, and if you are increasing the frequency value, that is nu1 is the first frequency, and nu2 is the second frequency, nu3 is the third frequency, that there is frequency increasing. For the frequency increasing, that actually mean the value of energy increasing. That is the value of energy h nu, right? There is a term of frequency in the equation of energy. So if you are increasing the frequency, energy increases, so that will increase, that will change, that will alter the value of stopping potential. So stopping potential will increase if the frequency gets increased. And for the final part, that is the fourth graph, the graph between frequency and stopping potential. This graph also can be represented with V0, that is stopping potential in the y-axis, and also kinetic energy, that is EV, in the y-axis. Now you can see that for lower frequencies there is no photoelectric effect, and so there is no case of stopping potential. And when the threshold frequency, that is nu0, reaches, you can have photoelectric effect there, and there comes the value stopping potential. And as the frequency increases, stopping potential also increases. That will be a straight line, right? From this you can find many things, like this equation is important. You know what is this equation? This equation actually comes from Einstein's explanation for photoelectric effect, that is h nu is equal to h nu0 plus EV0. From that you can rearrange that terms, and you can get this term, and this h by e actually is slope of this graph, right? This h by e is the slope of this graph, and if we are writing the equation like this, that is h nu minus h nu0 is equal to EV0, and it looks like this equation, that is equation for a straight line, y is equal to mx plus c, then h nu will be the slope, right? H nu, that is energy of the incident radiation, that will be the slope of this graph. And h nu0, what is h nu0? H nu0 is the y-intercept, and you can find the y-intercept from the graph, and that h nu0 y-intercept will be the value of photoelectric work function, right? Okay, now The next point is Einstein's explanation. That is a very important question. There can be derivation asked, and Einstein's photoelectric equation, we have just written that is h nu is equal to h nu 0 plus half mv square, or it is kinetic energy. Okay, right? Now derivation as well as some questions can be expected from this point, and the next one is loss of photoelectric emission. There are some loss of photoelectric emission, very simple part. You can easily make it by heart, and so don't skip this part. This is a very important part, very easy part. You should keep this point and this question in your mind. Now for the last part, failure of wave theory. There are many points we have learned why wave theory fails. Wave theory of light, why wave theory of light fails. From this point we can understand, or we can make a good idea of the dual nature of light actually. So for just a point, to make just a point, that when intensity of light increases, intensity of a wave increases, actually intensity of wave increases contributes to increase in intensity of energy actually, right? Energy increases, that will, but not in the case of photoelectric effect. The experimental observation of photoelectric effect shows this is not the case. So you have to study that, and that is for the chapter dual nature of matter and radiation. Thank you. I am handing over the session.
Okay, let me just summarize it. So as sir said, these are the important points: dual nature of matter and radiation. You know, you have to see de Broglie wavelength numericals. H is equal to lambda is equal to h by mv, or h by root of 2me. Based on that, you will have questions. Photoelectric effect, all the graphs are said. You know, these graphs are important. This graph is important. This one is important. This one is important, and this one is the most important, because they will ask you to draw this graph, and they will ask you to find the Planck's constant or the work function. How to get the Planck's constant? As sir said, this is y-intercept. Y-intercept is giving you h nu 0, which is the work function, right? Yes. And slope of the graph will give you h nu, from which you can find what slope of the graph is h. It is in place of mx. You know, slope of the graph is m, and which is h. They'll ask you to suggest a method to find the Planck's constant. Draw the graph, plot the values, and then find the slope. That will give you the Planck's constant. Okay, thank you, sir. Thank you very much. And next topic. Yes. We are moving to the next topic now. All right. So which is the next topic, sir? Actually,
I think it's atom, right?
Yeah.
Atom.
So we have the next topic here, atoms. The first thing is Rutherford's experiment, right? From Rutherford's experiment, what all things can be expected?
Geiger and Madsen.
The experiment has 4 names.
Yeah.
Geiger and Madsen experiment, Rutherford's experiment, alpha particle scattering experiment, gold foil experiment. Yes. We can expect the graph there.
Yeah.
We can expect the graph, number of particles scattered, angle of scattering, number of particles scattered with angle of scattering, and a numerical. Numerical is distance of closest approach. Alpha particle is coming closer to gold nucleus, and this distance is d. Kinetic energy turns into potential energy, right?
Yes.
So kinetic energy, yes. Kinetic energy is half mv square is equal to potential energy 1 by 4 pi epsilon 0 into 2e. Alpha particle 2e, and the gold charge of alpha ze divided by distance. You can cross multiply potential energy, distance only. Okay, distance only. So distance is taken to the left side. You can solve it to find the distance of closest approach. They'll give you kinetic energy. They'll give you the charge Z. If they say gold in the question, use 79. If they say silver in the question, say 47. Use 47 for Z, atomic number.
This question can be also asked like without alpha, proton and all.
Yeah. That also can come. Now you have to change this value, charge. Whichever particle is coming, you have to change accordingly. Okay. So anyway, that is an important numerical from that part. then Bohr's postulates.
Here also impact parameter too.
Impact parameter is also there. You know, impact parameter, you know, they'll ask direct question. You know, they'll ask you to find the perpendicular distance. That is actually impact parameter. The perpendicular equation is not needed. No. Just know that impact parameter is perpendicular distance between center and the velocity.
So when impact parameter is 0, angle of scattering is 180.
180.
When impact parameter is infinity, angle of scattering is 0, right?
0, yes. Yes, there is a statement, you know, the trajectory of the particle is decided by impact parameter. Why? Because lesser the impact parameter, more will be the deflection. Lesser the impact parameter, more will be the deflection. Yes, then we have Bohr's postulates. Bohr's postulates, there are 3 postulates. Electrons can revolve in certain non-radiating orbits called stationary orbits. Yes. Second one, in such orbits, angular momentum is nh by mvr is equal to nh by 2 pi. Then, quantization condition. And third one, electron might make a transition from higher energy to lower energy. In this process, the emission is h nu is equal to EI minus EF. Yes, energy difference. Okay. Then we have hydrogen spectral series and drawback. You know, hydrogen spectral series, this is what it is. You know, this is the general form. 1 by lambda is equal to R into 1 by NF square minus 1 by Ni square. Rydberg constant is R. And 1 by lambda is called angular wave number. Yes. Right. NF can take 1, 2, 3, 4, 5.
So final orbit.
Final. One is called Lyman, 2 is Balmer, 3 is Passion, 4 is bracket, 5th fund series. Yes. And they might ask you longest and shortest wavelengths. Longest by putting this number, first number. Shortest by putting infinity, series limit. You put Ni value infinity.
Shortest means greatest jump. That means infinity to percent.
Yes. Longest to shortest ratio also might be asked. Then know this, Lyman belongs to ultraviolet, Balmer to visible, Passion, bracket, fund to infrared. All of them to infrared. The number of spectral lines emitted is shortcut n into n minus 1 by 2. From a state n to a state, ground state, n into n minus 1 by 2. Yes. And equations for radius, orbital radius is given by n square by z.
I think, sir, you can show one example with this.
Yeah, if it is coming down from third state, it is 3 into 3 minus 1, 2. 3 into 2, 6 by 2. That is equal to 3. That means 3 to 1, 3 to 2, then 2 to 1. Look at that. One transition, second transition, third transition.
Okay. From 3, how many transitions are possible?
Transitions are possible.
Numbers.
That is important. Yes. And then the radius is n square by z, and velocity is 1 by 137 c by n into z. Okay. C is velocity of light. N is the quantum number, right? Z is atomic number.
And students can also by heart like the radius of the first orbit of hydrogen atom.
About Bohr radius, 0.53 angstrom. Okay. It is called Bohr radius. Velocity and energy is also given proportional to z square by n square. Z square by n square. Z is to be taken for hydrogenic atoms. Hydrogenic atoms are hydrogen, singly ionized helium, doubly ionized lithium, and triply ionized beryllium. Singly ionized, doubly ionized, triply ionized. All of these have only one electron each.
That's what we call hydrogenic atom.
Hydrogenic atom. Okay, so for such atoms, there is a limitation. You know, there is a limitation for Bohr model. You know, Bohr model could be applied to hydrogenic atoms only. Hydrogenic atoms only. I think we are done with it. Drawback of Rutherford's model and Bohr model. And here, the most important area would be Bohr's postulates. Rutherford experiment-based questions can come, or even Rydberg formula-based questions. And energy-based numericals are also important. Energy-based numericals.
So we can move to the next slide.
Move to the next slide now.
So nuclei.
Now nucleus. Nuclear radius is an important point. Nuclear radius is given by R is proportional to A raised to 1 by 3. Nuclear number R is proportional to A raised to 1 by 3. And there is this question which says nuclear density is a constant. Be it the lightest nucleus called hydrogen or one of the heaviest nuclei called uranium, same density. Nuclear density is very, very, very large. Okay, very, very large.
2.3 into 10 raised to 17.
2.3 into 10 power 17 kilogram per meter cube.
Sir, students can remember the range is 17, no?
17, yeah. After 23, you have to put 16 zeros to the right of it. Such a big value, right? If you take a teaspoonful of neutrons, that will weigh 10,000s of tons. That is why neutron stars are so heavy, right? Anyway, mass effect and binding energy problems. That is again very important. You know, nucleons combine to form a nucleus, yes. And when they combine, there is a reduction in mass. And find that mass using this ZMB. total mass of protons, right?
Total mass of
protons.
A
minus Z into Mn. Yes, A minus. This is total mass of neutrons minus mass of nucleus will give you
the mass defect.
Yes, mass defect.
Okay.
And then multiply this by 931.5, not C square, 931.5.
Then mega electron volt.
Yes, mega electron volt, because all these values are given in AMU, atomic mass unit. Okay, mass defect, binding energy curve, I'll come back to that later. Fission and fusion reactions. Learn an example for fission, chain reaction. You know, uranium is bombarded with neutrons, then it is split up into two nuclei, barium and krypton, right? Barium and krypton. Okay, there will be neutrons generated, and this will result in a chain reaction. Just learn that reaction. Uranium breaking into barium and krypton. Then fusion reaction also. Examples are given in the reader. You have to write at least 2 examples. 2 light nuclei combined to form a heavy nucleus.
So fission reaction is working principle of atom bomb.
Atom bomb or nuclear reactor, both. Controlled chain reaction is nuclear reactor. Uncontrolled chain reaction is atom bomb. Same thing that happened in Hiroshima and Nagasaki.
Yes. Fusion is energy generation in sun.
Stars, energy generation, sun, hydrogen bomb, thermonuclear bomb, all working principle fusion, thermonuclear fusion. Then binding energy, nuclear force graph and properties. Nuclear force graph, you know, potential energy or force taken here, the graph will be like this.
Very important.
It is very, very, very important. We would mark this as the most important questions from here. Excel.
They will ask to mark the very
attractive and repulsive. This part is actually positive, it is repulsive.
Yeah.
Positive forces are taken repulsive. And this part is negative, that part is attractive. So nucleons.
Yeah, sir, this value 0.8 femtometer.
0.8 Fermi. Femtometer, right? Yeah. If you bring the nucleons closer, now it is attractive. All of a sudden it turns repulsive. Okay. For the reason
0.8 femtometer.
Within that distance, for reasons which are not to be known. You don't have to know this. Nuclear force properties is also very important. Yes. Short range force, strongest force in nature. Just know this.
Irrespective of the charge.
Proton, neutron
will have same
force. And it is the strongest force. With 1 kilogram of uranium, you can ride a motorcycle for 15,000 years.
Yes, sir.
Just keep that in mind.
Yes,
so you will know that it is the strongest force. And again, it is saturated force, which means it is felt only in the immediate neighborhood. This neutron will attract or will affect the neighboring neutrons only, not the second layer of neutrons. Properties are important. Binding energy curve remains, right?
The binding energy curve.
Binding energy per nucleon is taken on y-axis. A nucleon number is taken on x-axis. 1 peak, 2nd peak, 3rd peak, and then 4th like this. Okay, first peak is for helium, 2nd is for carbon, 3rd is
30, right? 30.
This is between 30 and 170. Between 30 and one by one we will see the inferences. This is helium, this is carbon, this is oxygen, and maximum is for iron. There are 4 inferences. Number 1, helium, carbon, oxygen have peaks, which means their binding energy per nucleon is more, right? More. And between A equal to 30 and A equal to 170, graph is almost constant. 5.5 million electron volt.
Atom will be most
iron 56.
8.3 mega electron
volt. Yes. And last nucleus, uranium, has less binding energy per nucleon in comparison with the neighbors. There are 2 important inferences. Trust me, this is going to come. You know, in fission, light nuclei, hydrogen, combine to form helium. Binding energy per nucleon increases. Okay, that means release of energy. In fission, uranium will break into barium and krypton. There also binding energy per nucleon will increase. So both cases, fission and fusion, binding energy per nucleon increases, which means release of energy. So how do they ask a question? They will ask, how do you explain the fact that energy is released in fission and fusion? Okay, in fusion, hydrogen and hydrogen combine to form helium. Right. In fission, uranium breaks into barium and krypton. Lighter nuclei. Yes. Even then, binding energy per nucleon.
Middle range is like comparatively binding energy per nucleon is more. So binding energy nucleon is directly proportional stability. Stability is more in this region. Here less stable, here less stable. So that's the nuclear fission and fusion reaction principle.
Then they can ask one more question. They'll ask you which one is more stable. They will give you 2 elements. How do you find it? You find using this you find the mass defect. for each element. For example, if they give lead and something else, find it for lead, multiply by 931.5, then mega electron volt. Divide that by mass number, you will get binding energy per nucleon. The more binding energy per nucleon, the more is the stability. The more is the stability.
Binding, not binding energy proportional stability. Binding energy
per nucleon should proportional to stability.
Binding energy by mass number you have to find which has more, that has more stable. Okay?
Yeah.
Keep in your mind.
Now this is all about nucleus.
Nuclei.
You know,
sir, this is
the most important question. Show that nuclear density is constant.
So you want to by heart the value also. Density of the nucleus is 2.3
into raised to 17 kilogram per meter cube.
MCQ might come.
Also, this graph is very important. This binding energy curve is important. Mass effect binding energy. Then nuclear forces properties. Nuclear force graph. Okay, I'll repeat those points one more time. We will repeat. First is nuclear density is a constant. You have to prove it. Second is mass effect binding energy problems. Binding energy curve. Then nuclear force.
You can do one sample questions binding energy problem. Okay. M into 931.5. Mass effect you should find, multiply 931. You will get mega.
In yesterday's live sessions we have done it. You can check it out on YouTube. Okay. Binding energy curve. And then nuclear force graph properties. All these are important.
Easy question only comes from.
Easy question. And that's all about all atoms and nuclei. And Anas sir and Ravi sir will explain the important questions from.
You and Anas sir should take the semiconductor. Right?
Yeah, semiconductor sir, please.
Thank you, sir. Now, this is the 14th chapter. That is the last chapter of our physics, and that is electronic devices. Electronic devices and semiconductors, and there will be the question from band diagram. What may be the questions from band diagram?
Yeah, they might ask, like, they will ask you to draw the band diagram for conductors, insulators and semiconductors. Yes. And they might even ask intrinsic semiconductors, extrinsic semiconductors also.
And comparison of band
comparison
diagrams.
of conductors, right? Insulators and semiconductors on the base of band theory. That's an important question. Yes, sir.
Now the second one, P and N type semiconductors. That's an important question, right, sir?
Yeah, P and N type, they'll ask you to briefly explain or compare P and N type semiconductor materials. So you just have to write a note on it, and there is an equation also.
Very important equation.
If a numerical comes, it's going to be this equation, right?
Number of electrons into number of holes will give you intrinsic carrier
concentration. Ni is intrinsic carrier concentration.
Squared.
Ne is number density of electrons. Nh is number density of holes. If a numerical comes, 100% sure it is going to be on this equation, because there is no other equation in this chapter. Okay, right. Now,
right, sir?
Yeah, sir has already marked the red in red. Why?
Very important question.
It is important. One of the most important questions, one of the most repeated questions, right?
Formation of a PN junction.
Yeah,
right?
Formation of a PN junction. It is actually done in 4 steps. You know, that is very important. Yes, Anas sir, that is important. Then what? We have
forward bias and reverse bias. The diagram can be asked, and also the characteristics of forward bias and reverse bias.
The graph is also important. Graph. Just sir, graph. You will just give an idea of the graph also. Forward bias and reverse bias.
Current, please remember, current here is milliampere. This range of current will be
here it is microampere. Reverse bias microampere, because reverse current is due to minority carriers. Minority carriers are less in number. That's a previous question. Why do we take microampere on y-axis? Because minority carriers are very less in number, and minority carriers create reverse current. It is less. That is why micro there, milli there.
This is the characteristics of forward bias.
Yes, it is
and the voltage, knee voltage will be
knee
here.
Knee voltage or breakdown voltage or threshold voltage. There are 3 names for it.
Only after the threshold voltage we can see the significant change in current.
Yes. And
the last part, the reverse cara will be like this.
Yeah, that point is also important.
This is the breakdown voltage.
Yes, breakdown voltage. It is important, breakdown voltage. And this current also is important, saturation current. This current is called saturation current, right? That current is called saturation current, and they'll ask it, and they may ask this question also: why is it constant there, or why is the current rising sharply? Right, they are also important questions. Okay.
We have covered this, and for the next point, that's diode numericals.
So just show a diode numerical, sir, because that will be good for them. Because
short one.
Right. 6.
Yes.
for diode numericals, this can be a question, and this is the diagram. If they are asking this question in like this diagram, that will be this diode, and the other diode is given, and it is connected to a cell. And from this diagram itself, we can see that this diode is in forward bias and this is in reverse bias.
Yes. This is forward bias because P region is connected to positive. Yes. And this is reverse bias.
This
right?
is in reverse bias.
Yes.
So it will not conduct. This section of the diagram will not be considered, and only this condition, by using Ohm's law, we can find the value of current.
Yes. This question has come many times. It's very important. Okay.
Very
you have
important
to find
question.
the current. Very important question. You have to find the current. Yes. Then what else is there in this topic?
Now,
Yes.
for the last part, rectifiers.
Yes. Very important. As Rafisa says, it is a five-star rated question because it is so important. Half wave rectifier and
full wave
rectifier. Both types of rectifiers would be asked in examinations. They are very important. Okay. So anything to add, Rafi sir? Anything to add to this?
That rectifier, no?
Yeah.
Full wave rectifier, my mind is saying that this time full wave rectifier sure will come, including the waveforms, okay? Waveforms. You want to know the waveforms?
And the filters
only. Yeah, a student who are not learned sufficient in physics must learn this one. You will get that 5 mark area, 7 mark weightage,
sure.
100% sure. Okay, rectifiers and filter circuit, just a circuit only needed.
Circuit only.
Explanation.
Do not learn in detail.
And I think, sir, we can add this point also.
Diagram is needed in filter circuit.
Diagram
so in half wave rectifier, suppose the frequency of input is 50 Hertz, what will be the output frequency?
That's also 50.
Okay, just an easy question only. What's the output frequency?
That is also.
It's a half wave rectifier, so frequency will be same, right, sir?
Yeah,
it's 50 Hertz.
Frequency of ripples will be 50.
It's 50 itself. Okay, if the input is 50, then output is also. If the input is 100, output is also 100. For a full wave rectifier, sir, double, right?
Double, because every cycle output comes twice.
Yeah.
So ripple frequency will be 100.
Okay, so whatever the input frequency they are given for full wave rectifier, take the double, right, sir?
Yes,
so it's become 100. That's the 1 mark usually comes from this part.
Yeah.
Okay, sir, we are expecting energy band diagram.
Energy band diagram, and the most important points are energy band diagram, PN junction formation,
PN junction formation,
rectifiers.
Yeah,
and
diffusion and drift here, no?
Yeah,
diffusion and formation you want to explain.
There are 4 steps: diffusion, drift, explain everything. That's a 3 mark question.
Yes. That's all, sir, about this one.
So we have covered all the chapters. This is it. And over the last couple of days, we have done all types of numericals. And if you haven't watched them, just go back and watch them. All the sessions are done with carefully selected questions. 100% sure if you watch these sessions and if you do this checklist today, you are going to get the questions.
We can explain, sir, from the checklist. If you cover properly, I think the guys will get 80% more in physics easily, right? Sure. Must to do this, okay? We covered all the importance.
Everything is covered. And from Excel, all from the right, from the bottom of our hearts, we wish you the very best. Do not be afraid of anything. This is your battle. You're going to win it tomorrow. No, nothing is going to harm you. Nothing is going to come in front of you. Now, you're definitely going to rock tomorrow. Physics is going to be the easiest for you. Physics is going to be the highest scoring exam for you. End of the day, we will win. We are going to make it.
Yes.
All the best. All the prayers from Team Excel here. Thank you very much. Thank you for
staying with us for the entire year. Okay.
Thank you very much.
All the best.
All the best. See you then.
Thank you all.
Bye. Thank you.
Yeah.
Bye.